Hi, I'm Ben-Yaakov. This presentation is entitled Deciphering Switching Noises in PWM Converters. The issue of this presentation is noise. Workers in power electronics are accustomed to seeing waveforms like this, oscillations, spikes, which are very irritating. The objective of this presentation is to show how some of the spikes and oscillations are generated during the switching processes of hard-switched PWM converters. I'm going to use this circuit as a basic unit to test and to simulate. This is actually a generic cell that is found in just about any PWM converter. Like this could be a synchronous buck converter, could be a synchronous boost converter. Now the fact that during the dead time the body diode of this transistor, say, is conducting would mean that this is also applicable to non-synchronous system. Obviously, this is also related to a inverter in which the current might be going one way or the other, like a sinusoidal waveform. So this is a very basic unit that tells us a lot about PWM converters. Now here we have a high side transistor, we have a low side transistor, and this will be the midpoint. I'll refer to it. And here we see the gates of the low side, the gate of the high side. This is the green one, and this is the midpoint here between the two transistors, and this is the current, and in this case it's an inductor, so it's an inductor current. Let me point out that the waveform that are presented here that have been measured are not on exactly this circuit. The circuit is different, although it's similar, but it's not one-to-one. So we should treat these measured waveforms just as a reference, not an actual measurement of this circuit. Now I'm going to concentrate on a situation in which we have an outgoing current here. This transistor has been on, and therefore the current is passing through the transistor, and then it's turned off, so the current will be passing through the diode, and then we're going to turn on the high side transistor. This is the worst case in terms of oscillation and noise, so I'm going to concentrate on this particular situation. So in this case, we're going to have a problem with diode recovery, because as the diode is passing through the diode and this transistor is turned on, we have a problem here of reverse recovery. And also we're going to charge all these capacitors, the parasitic capacitor of this transistor, so it's going to be quite a bit of a transient here. Now the default situation is R on 20 ohm. This is for this drive circuit. We have a classical drive circuit with an on resistor which is larger than the off, the turn off resistor. The on will be 20, the off will be 5, and the rise and fall time of these generators, and the default is that all inductances are very small, 1 femto value, which is 10 to the minus 15. So this is the default value. I'm going to change them later on. Now what we have here is the transistor with its internal inductances. This LG actually will represent both the internal and the external inductance of the line feeding the gate. And then we have a bus inductance, which again the default value is 0 as a matter of fact. And of course the transistor, the model of the transistor includes the parasitic capacitances between the gate drain, gate source, and drain and source. So this is taken from the library for this particular transistor. The voltage in this simulation is going to be 50 volt. And I'm going again to run simulation in which I'll change or add inductances to see the effect of these on the operation. So let's start with the default case. There are no inductances, and here is what we see. These are the gates. This is the low side gate going down. Again, it was on, transistor was conducting, now it's going down. The diode will be conducting. And then we have the high side turned on. We have here the Miller plateau. There is a so-called Miller spike at the low side due to the swing of the voltage at the midpoint. This is actually the midpoint, and therefore we see a injection through the parasitic capacitance as there is a swing here. There's a step voltage through this capacitance. We're going to have some disturbance here, and I can see it here, which is also manifested here also at the high side. So this is the midpoint, and here we see the current. This is actually the reverse recovery current, and with no inductances at all, no added resistances, then it comes up to be 200 amp. This is of course an exaggeration. In a real circuit, usually you will not see it for the reasons we'll see later on. So again, this is the ideal case, no parasitics, and using the default parameter. Now I've changed the rise time of the drive signal to be 10 nanoseconds instead of 100, and the on resistor to be 1 ohm. That is, it was 20 and now it's 1 ohm. This is the resistor here R1 for turn on of the gate. So in this case, due to the fact that the rise time is much faster, reverse recovery becomes extremely large, and this is in fact the reason that we don't like to have the on resistor to be small. We like to have it moderate so as to lower down the rate of rise and therefore to lower this spike of the reverse recovery. Now, what about the gate inductance? Okay, this is the next step I'm going to examine, and that is the inductance here, which will be, say, the drive inductance plus some of the internal inductance within the element itself. If I just change the inductance to 3 nanohenry, everything else is default, I don't see any big difference. And the reason is that to see a big difference, or to see any difference, the Q, quality factor of the drive circuit, has to be higher than 1. Now, the value depends on the characteristic impedance, Lg over Cn square of this. Lg is the inductance, C is the input capacitance, the equivalent input capacitance of the transistor, and Rg is the resistance in the loop. Now, if this Q is low, we don't see any difference. Now, in order to enhance it, what I did, I changed R1 to be 0.1 ohm and Lg 50 nanohenry, which is of course quite a bit, just to enhance the effect. And indeed, what I see here is this overshoot, very typical of an inductance in the drive loop. And this again will depend on the Q factor. And since this transistor I'm using in the simulation has quite a bit of input capacitance, this inductance has to be large in order to see any effect. So in this particular case, the inductance of the gate is perhaps not too much of a problem. Now I'm going to examine the effect of the bus inductance. I'm going to change this to 1 nanohenry. So now the source, the bus, is connected to the transistor via the 1 nanohenry. Of course, if you have an internal inductance, which you always have, then you can't see from outside the effect of this inductance on the transistor because you cannot get to this point. So this actually, what we're going to see is not just the voltage across the transistor, but actually across the die. So even if you don't have any inductance here, there is some inductance here, and there is always some disturbance on the die itself. So this is a very important parameter to consider. So here it is, and as you can see, this is quite remarkable. And the reason for this oscillation is that as we have the current passing here, charging this inductance, then due to the interaction of this inductance with the capacitances in the circuit, you're going to have a resonant circuit. And this is the effect of the resonant circuit. And you see that it causes quite a bit of disturbance. It causes a high voltage press on the transistor, and it actually propagates into the gate side through the parasitic capacitance. So bus inductance is very, very bad. So one should make an effort to make the inductance as low as possible. Now I'm going to make another change. Again, I've made the bus inductance almost zero, and then I'm going to put inductances at the source of the transistor. This could be an internal inductance in connecting the bonds, connecting the die to the output terminals, to the actual terminals of the device, and also can represent some of the interconnection inductances, which I'm showing here. And this sort of represent everything, okay? So I've put the inductance for the high side and low side transistors, and these are 0.3 nanohenry, both of them. And here I see something very, very typical, and in fact it's very similar to what we've seen in the measurement. We see that we are going to have an oscillation during the sort of Miller plateau. That is when the transistor is conducting, okay? So we have here this oscillation, which is shown here on the drain, and also we're going to see them in the gate side, and in fact also reflected to the low side. This is the yellow is the low side. I'm sorry, this one is the low side. The green is the high side, which is turned on. So what is the reason for this oscillation? Well, the reason is that when the transistor is in the conduction area, that is when the voltage is swinging, then the transistor is in a linear mode. In this case, you have amplification between gain and drain, and the capacitors, the parasitic internal capacitances, plus the inductors, and the fact that it is within the linear region makes it, as a matter of fact, an oscillator. So we have here an oscillator that you can actually analyze depending on the values of these elements, and this actually oscillates during this transition, and the oscillation, of course, will be a function of the inductances that you have in the circuit. And as it turns out, this one becomes a very, very important because you have feedback here to the gate, okay? So you have actually the voltage across this inductance is sort of being fed back, so the whole thing is starting to oscillate. So this inductance plays a major role in initiating this oscillation, and therefore you'd like it to be as small as possible. And I'm just hinting that this is one reason we are using the Kelvin connection, which I'll talk about it later on. So let's go back now to the circuit, and we understand now this oscillation, which reflects here due probably to the fact that there is also a bus inductance in the actual physical circuit that these waveforms were taken off. And also we see here some oscillation of the inductor. Now, if this would have been an ideal inductor, you wouldn't expect to have any changes in the current. So what could be the reason? So let's have a look now. What happens if you do have an inductor? If you have an inductor, and I'm assuming here 100 microhenry, and I'll run this circuit with the default values, here is what I'm getting. I see the following. This is what we have seen before, nothing new. This is the inductor current, very smooth because it's a large inductor, and obviously you wouldn't expect to see changes in the current in the scale of microseconds or nanoseconds, because for that you need high voltages, very high voltages. So we don't see it here. But if I add a parasitic capacitance to the inductor, which you will always have because this represents the interwinding capacitance of an inductor. This is why we have the resonant frequency of the inductor. This capacitor is a lump representation of the distributed capacitance that we have within the windings. We see this waveform and we see this current now. I've added the current, of course, of the capacitor to the current of the inductor itself, the pure inductor, and we see this disturbance. So we can explain some of the disturbance that we have seen in the actual measurement due to the fact that current is passing through the parasitic capacitance. However, the nature of these oscillations is a bit different, and again, as I've mentioned earlier, this is not taken off the circuit that is shown here in the simulation. It's a different circuit. So this could be the reason why we have the lower frequency. And also there is another point here. The current was measured with a probe. Now the probe is prone to interferences, to noise injected from outside into the opening of the probe. So therefore, some of this could be just measurement error, not actual current that you measure, but rather something which has been injected as a measurement error. Now, up to now, we talked about the worst case. Now, let's just have a glimpse at the case which is the best part of the switching, and that is when we have the current passing through the transistor, the upper transistor, and we turn the transistor off. Then there is a natural commutation of the voltage here until this diode is conducting, and only then we turn on the transistor in what you might call zero voltage switching. So this is the best part of the switching cycle, and we see here the gate of the high side going down, this gate here, and there is this swing here of the midpoint, and then we see that very smoothly we turn on the low side while this diode is conducting. So this part really causes no big problem. The other part of the hard switching with the reverse recovery of the diode is the main problem causing oscillations. So what can be concluded here? Switching noise in PWM converters are due to parasitic inductances and capacitance. This is clear. A major cause of gate oscillation is inductance at the source of the MOSFET. This is the main problem because this causes oscillation in the linear region. So Kelvin connection could help to moderate these oscillations. And here I'm showing a schematics of the Kelvin connection. The regular connection is when you have the return of the gate signal connected to the output leg, to the source. This could be directly to the component itself, to the device, or maybe on the PCB. In any event, you do have inductance of the internal inductance of the device plus external inductance that you might have. And as we have said, this causes oscillation. Now, if, however, I have another connection to the die itself and hook up the return to this connection, this will help a lot. The reason is that although we do have here also inductance, as we have here, there is no amplification here. That is, in this inductance, when you have a small current, the current here becomes much, much larger because here we have the current of the drain, while here we have only the current of the drive loop, and therefore, although it's adding inductance, as we have seen it before, it's like an inductance here, it doesn't matter, but the effect is much, much smaller than this effect in which you have amplification. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it'll be useful to you in the future. Thank you very much.